You're listening to the Bare Metal Cyber Prepcast, created to help you succeed in your educational journey. Learn more at baremetalcyber.com, where additional prepcasts, books, and training materials await. Let's get started. Tabular reasoning refers to the ability of artificial intelligence systems to analyze, manipulate, and interpret structured data organized into rows and columns. Unlike unstructured text, tables present information in a compact and systematic form, where relationships between values are implied by their position. A number in one cell may depend on another cell's formula, or a row may summarize an entire transaction. Humans excel at reading these structures, effortlessly recognizing headers, identifying totals, and comparing entries across columns. For AI, however, tables pose distinct challenges. Language models trained primarily on narrative text often misinterpret the structure, treating values as words rather than numeric or relational entities. Tabular reasoning therefore requires specialized approaches, where AI systems are adapted to recognize the logic of tables, spreadsheets, and relational data. This ability is essential for tasks like financial auditing, regulatory monitoring, and business reporting, where structured accuracy matters more than stylistic fluency. The importance of tabular reasoning in enterprises cannot be overstated. Across industries, structured data forms the backbone of operations. Financial institutions track every transaction in ledgers and spreadsheets. Healthcare organizations maintain patient records in tabular formats. Scientific research organizes experimental results into rows and columns for analysis. Even small businesses rely on spreadsheets to manage inventory, payroll, and budgeting. Because so much decision-making rests on tabular data, the ability to analyze it reliably is critical. Errors in reasoning over tables can lead to costly financial miscalculations, flawed compliance reporting, or dangerous misinterpretations in medical contexts. This is why enterprises increasingly look to AI systems that not only handle free-flowing text but also reason correctly over structured information, ensuring that outputs align with the precision required in professional workflows. Challenges for AI in tabular reasoning stem from the mismatch between text-trained models and numeric or symbolic data. Language models excel at generating coherent sentences but often falter when asked to calculate totals, apply formulas, or maintain relational integrity across rows and columns. They may misread a number as a token rather than a value, or they may ignore the significance of headers that define relationships between data points. Furthermore, tables often embed domain-specific conventions, such as financial ratios or medical codes, which require specialized knowledge. Without additional tools or adaptations, models may hallucinate results, inventing numbers or formulas that look plausible but are unsupported by the data. This creates risks in high-stakes domains, where even a small numerical error can have cascading consequences. The challenge then is not only technical but conceptual, aligning AI reasoning with the structured logic that tables embody. Specialized models have been developed to handle tabular input directly. These models incorporate structural awareness, treating rows, columns, and cell relationships as integral to the data, rather than as arbitrary sequences of tokens. Some approaches embed tables into graph structures, allowing the model to reason about connections explicitly. Others integrate symbolic components, combining neural language understanding with rule-based reasoning for arithmetic and logic. By adapting architectures to recognize the unique structure of tables, these systems outperform generic models in tasks like SQL query generation, table-based question answering, or spreadsheet manipulation. They demonstrate that reasoning over structured data requires more than brute force scale. It requires designs tailored to the medium, much as image models are tailored to pixels and vision. Spreadsheet applications extend tabular reasoning into one of the most familiar and widely used tools in modern work. Spreadsheets allow users to define formulas, reference cells, and apply operations that generate dynamic outputs. Understanding spreadsheets, therefore, involves not just reading values, but recognizing relationships defined through formulas and dependencies. For example, a cell might compute sales tax as a percentage of another cell, or a pivot table might summarize entire datasets. AI systems must grasp these relationships to provide meaningful assistance. Spreadsheet reasoning involves both symbolic manipulation and contextual interpretation, blending language understanding with computational precision. By mastering this space, AI can assist not only professional analysts, but everyday users who rely on spreadsheets for personal finance, education, or small business operations. Integration with external tools is essential for effective tabular reasoning. Language models alone cannot reliably perform precise calculations, statistical analyses, or database queries. Instead, they benefit from tool augmentation, where queries are routed to calculators, databases, or statistical engines that provide accurate results. For example, when asked to compute a sum or average across a dataset, the model can delegate the calculation to a specialized tool, ensuring correctness. Similarly, when analyzing relational data, integration with SQL engines allows queries to be executed reliably. This hybrid approach combines the flexibility of language models with the rigor of formal systems. It reflects a broader principle in AI. Reasoning over structured data is most effective when natural language interfaces are paired with precise computational backends. Common tasks in tabular reasoning illustrate its practical importance. Summarizing tables into natural language narratives allows users to grasp key trends without scanning every row. Detecting anomalies highlights unusual entries, such as fraudulent transactions or abnormal lab results. Answering natural language queries about data enables intuitive access, where users can ask, "What was the highest revenue month last year?" rather than writing formulas themselves. These tasks rely on accurate mapping between language and structure. Each requires the system to respect the integrity of the data, ensuring that answers are derived from actual values rather than plausible guesses. The diversity of tasks demonstrates that tabular reasoning is not a single capability but a collection of interdependent skills, each vital for transforming raw numbers into actionable insights. Evaluation metrics provide benchmarks for measuring success in tabular reasoning. For spreadsheet tasks, accuracy in generating correct formulas or referencing the right cells is a critical metric. In database contexts, correctness of SQL queries serves as a standard benchmark. Task-specific datasets, such as wiki table questions or Spider, provide structured ways to assess performance on table question answering and SQL generation, respectively. Metrics must capture both correctness and relevance, since a query that executes without error may still return the wrong information. By grounding evaluation in objective outcomes, whether the answer matches the data benchmarks ensure accountability. They also highlight gaps, such as struggles with complex joins or nested formulas, guiding further research. Evaluation in tabular reasoning is not just about fluency, but about fidelity to structured logic. Risks of hallucination remain a persistent problem. When models are asked questions about tables, they may sometimes invent values not present in the data. For example, if asked for a total that requires summing a column, a model without access to calculation tools might guess a number based on pattern recognition rather than actual arithmetic. While the answer may look plausible, it undermines trust and can lead to harmful outcomes if users rely on incorrect information. Hallucination is especially dangerous in finance, healthcare, and compliance, where fabricated outputs can have real-world consequences. Guarding against this risk requires careful system design, tool integration, and explicit checks to ensure that answers derive from data rather than imagination. Preventing hallucination is therefore central to making tabular reasoning systems reliable in practice. Bias in tabular data introduces additional concerns. Datasets may reflect sampling errors, measurement biases, or structural inequities. For instance, financial datasets might underrepresent transactions from marginalized communities, or healthcare datasets may reflect biases in clinical practice. AI systems, reasoning over such tables risk amplifying these biases, presenting skewed results as objective truth. Recognizing and mitigating bias requires awareness of how data was collected as well as mechanisms for auditing outputs. Transparency is essential. Users must understand that even structured data is not free of distortion. By embedding fairness checks and monitoring, developers can ensure that AI systems do not simply inherit and amplify existing inequities. Bias management in tabular reasoning is as important as accuracy, since the appearance of objectivity in numbers can mask deeper social biases. Scaling challenges emerge as datasets grow larger. Small tables can be processed directly, but enterprise datasets often contain millions of rows and hundreds of columns. Handling such scale requires indexing, efficient queries, and distributed computation. Systems must balance completeness with efficiency, deciding when to summarize, sample, or offload processing to external engines. Scaling also introduces storage and infrastructure costs, demanding careful design to ensure sustainability. Without scalable architectures, tabular reasoning systems risk becoming bottlenecks rather than accelerators. The challenge lies in maintaining both accuracy and responsiveness as datasets expand, ensuring that insights remain timely and relevant even at industrial scale. Enterprise relevance underscores why investment in tabular reasoning continues to grow. In finance, accurate table analysis supports auditing, fraud detection, and compliance reporting. In healthcare, structured reasoning ensures reliable interpretation of patient records and laboratory results. In government, spreadsheets underpin budget allocations and regulatory oversight. Each of these domains depends on structured accuracy, where errors can carry severe legal, financial, or human consequences. Enterprises seek AI systems that do not merely approximate reasoning but provide verifiable, auditable outputs. Tabular reasoning, therefore, is not an abstract research goal but a practical necessity, supporting critical infrastructure in nearly every sector of the global economy. Safety concerns arise because mistakes in tabular reasoning can propagate downstream. An incorrect formula may produce faulty financial statements, a misinterpreted lab result may lead to incorrect medical decisions, or a flawed compliance report may expose organizations to legal risk. Unlike creative text, where errors may be stylistic, tabular reasoning errors are often silent but consequential. Systems must therefore incorporate safeguards such as validation checks, redundant verification, and clear uncertainty reporting. By making limitations visible, AI systems can help users recognize when results require additional scrutiny. Safety is not about eliminating risk entirely, but about managing it responsibly, ensuring that the benefits of automation do not come at the cost of trust or reliability. As structured reasoning matures, the natural next step is integrating with broader mathematical and symbolic tools. Just as tabular reasoning requires accuracy and precision, so too do mathematical models and symbolic reasoning systems. By linking these domains, AI can extend its reach from spreadsheets and databases to more complex forms of structured analysis. The connection reflects a shared foundation: the need to translate human intent into machine-executed precision. Tabular reasoning thus serves as a gateway, preparing systems for increasingly sophisticated tasks where structure, accuracy, and accountability are paramount. It is not merely about managing rows and columns but about embedding reliability into the broader ecosystem of AI reasoning. For more cyber-related content and books, please check out cyberauthor.me. Also, there are other prepcasts on cybersecurity and more at baremetalcyber.com. Formula generation is one of the most direct and impactful applications of tabular and spreadsheet reasoning. Many spreadsheet users, from finance professionals to students, rely heavily on formulas to calculate totals, averages, and more complex relationships. However, crafting the correct formula often requires technical expertise in spreadsheet syntax, such as understanding when to use sum versus sumif, or how to reference ranges across sheets. AI systems trained for formula generation bridge this gap by converting natural language instructions into accurate formulas. For example, a user could ask, "Calculate the total sales for January where the region is North America," and the system would produce the appropriate conditional aggregation. This ability democratizes spreadsheet use, lowering barriers for individuals who may lack technical proficiency but still depend on data analysis. Reliable formula generation ensures that spreadsheet automation becomes more accessible and less error-prone, directly improving productivity in both casual and enterprise settings. SQL query generation extends this principle into database environments. Just as formulas define logic in spreadsheets, SQL queries define operations in relational databases. Writing accurate queries requires knowledge of schema structure, SQL syntax, and relational logic skills that not all business users possess. AI models enable natural language to be translated into structured SQL commands, allowing a user to ask, "Which customers purchased more than 5 items last quarter?" and receive a valid query. This capability empowers non-technical staff to access insights directly rather than waiting for database specialists, reducing bottlenecks in organizations. It also supports developers by accelerating query writing and suggesting optimizations. SQL generation underscores the broader goal of tabular reasoning, creating intuitive bridges between human questions and structured data operations. By making database access conversational, AI brings relational analysis to a wider audience while still supporting experts with precision and speed. Data transformation tasks highlight another strength of tabular reasoning systems. In real-world workflows, data rarely arrives in the exact format required for analysis. Rows may contain duplicates, missing values, or inconsistencies in units and formatting. Columns may need to be combined, split, or relabeled. AI systems can automate many of these cleaning and transformation processes, applying filters, normalizations, and aggregations based on user instructions. For example, an analyst might request, "Remove all rows with missing values in the revenue column and calculate the median revenue by product line," and the system could generate the appropriate sequence of operations. Automating these repetitive tasks saves time, reduces human error, and ensures consistency across datasets. Data transformation is the unsung foundation of analysis. Without it, results are unreliable. By assisting in this step, AI adds value not just in producing answers, but in preparing data responsibly for deeper reasoning. Summarization of tables allows users to grasp large datasets quickly by highlighting key patterns, anomalies, and trends. For example, a sales table with thousands of rows can be summarized as, "Revenue grew by 12% in Q2, with the highest sales in the electronics category, while the Midwest region underperformed relative to last year." Such summaries transform raw numbers into narratives that support decision-making. Summarization can also highlight outliers, such as unusual values or errors that warrant further investigation. Effective summarization requires both quantitative accuracy and linguistic clarity. The system must calculate correctly while also phrasing the insights in natural, accessible language. This balance mirrors how human analysts present findings, but AI allows it to be done at scale and speed. Summarization reflects a broader principle of reasoning. Raw data becomes meaningful when transformed into patterns and stories that humans can interpret and act upon. Integration with business intelligence platforms amplifies the impact of tabular reasoning by embedding AI insights into dashboards and decision-making tools. Business leaders often rely on visualizations and metrics to guide strategy, but creating and updating these dashboards requires technical effort. AI-enhanced reasoning systems can generate charts, populate dashboards, and even recommend metrics based on the underlying data. For example, they might suggest highlighting customer churn rates or visualizing revenue by geography. This integration allows organizations to move from static reporting to dynamic, AI-driven intelligence. It also reduces the gap between data storage and actionable insight, enabling faster and more responsive decision-making. In this way, AI augments traditional business intelligence tools, making them more conversational, adaptive, and aligned with the questions stakeholders actually want answered. Evaluation benchmarks provide a structured way to measure tabular reasoning performance. Datasets such as Wikitable questions test models on answering natural language queries about semi-structured tables, while Spider focuses on evaluating SQL query generation. These benchmarks expose system strengths and weaknesses, guiding researchers and developers toward meaningful improvements. For instance, a system may perform well on straightforward queries, but falter when handling nested conditions or joins. By comparing results across benchmarks, organizations can select tools suited to their needs, whether they prioritize simple summarization or complex relational reasoning. Benchmarks also ensure accountability, preventing inflated claims of accuracy by grounding evaluation in standardized tests. Just as in language or vision domains, shared benchmarks in tabular reasoning drive innovation through transparency and comparability. Applications in healthcare illustrate the high stakes of reliable tabular reasoning. Patient records, laboratory results, and treatment histories are often stored in structured formats that must be interpreted precisely. An AI system that miscalculates dosage schedules or misinterprets lab results could pose real risks to patient safety. At the same time, accurate tabular reasoning can accelerate care by flagging anomalies, detecting correlations, or supporting predictive analysis. For example, I might identify patterns in lab data that suggest early onset of disease, prompting preventative treatment. It might also summarize patient histories for physicians, saving time and reducing oversight errors. Healthcare shows both the promise and responsibility of tabular reasoning. It can enhance clinical decision-making, but only if implemented with rigorous safeguards against error and bias. Educational applications provide a different perspective, where the emphasis is on learning and exploration rather than operational reliability. Students often encounter tables in subjects like mathematics, economics, and the sciences, but interpreting them correctly can be challenging. Tabular reasoning systems allow learners to query datasets in natural language, explore relationships, and receive explanations. For example, a student might ask, "What does this table show about the relationship between study hours and test scores?" and receive both numerical analysis and an interpretive explanation. By making data more approachable, AI supports inquiry-based learning, encouraging students to experiment with questions and see the results directly. This fosters data literacy, a skill increasingly essential in modern society. By bridging raw tables with natural explanations, educational applications of tabular reasoning cultivate curiosity and comprehension simultaneously. Cost considerations are important in assessing the viability of tabular reasoning systems. Unlike long context language processing, which can be computationally expensive, structured data operations are often more efficient. Summarizing a table or generating a SQL query requires fewer tokens and less memory than processing thousands of words of narrative text. This efficiency makes tabular reasoning particularly attractive for large enterprises managing massive datasets. However, costs are not eliminated entirely. Training specialized models, integrating with databases, and maintaining secure infrastructure still carry expenses. Organizations must weigh these costs against the savings from automation, reduced error rates, and faster insights. The economics of tabular reasoning generally favor adoption, as the return on investment is clear when systems improve accuracy and speed in domains where mistakes are costly. Limitations of AI in tabular context remind us that models alone cannot substitute for statistical reasoning. While systems can generate queries, formulas, or summaries, they often lack deep understanding of variance, significance, or uncertainty. For example, an AI might report a correlation between two variables without recognizing that it is statistically insignificant. This highlights the importance of integrating explicit statistical tools and methods into tabular reasoning pipelines. Without such integration, AI risks producing outputs that are numerically correct but analytically misleading. Limitations also extend to edge cases, where rare or unusual data structures may confuse systems. Recognizing these boundaries ensures that humans remain responsible for high-level analysis, using AI as an assistant rather than a substitute for rigorous reasoning. Research directions point toward combining symbolic logic with neural tabular reasoning. Symbolic approaches excel at precision, ensuring strict adherence to logical rules, while neural networks offer flexibility in interpreting ambiguous human input. By combining the two, researchers aim to create systems that can interpret natural language queries while guaranteeing logically sound outputs. For example, symbolic components could ensure that generated SQL queries always respect schema constraints, while neural models interpret the intent of the question. This hybrid approach promises both accuracy and usability, addressing current gaps where models hallucinate or misapply logic. The integration of symbolic and statistical methods reflects a broader trend in AI, moving towards systems that balance flexibility with rigor. Integration with agents is an emerging frontier. Agents that handle complex workflows often need to interact with structured data, whether for compliance, reporting, or analysis. Tabular reasoning equips agents with the ability to query databases, transform spreadsheets, or summarize reports autonomously. For example, an enterprise agent might generate a compliance report by extracting values from financial tables, applying formulas, and drafting summaries for auditors. Integration ensures that tabular reasoning is not siloed but embedded within larger workflows, where structured data is central. This convergence demonstrates how reasoning over tables is not just a standalone capability but a vital component of multi-step AI agents that support human decision-making in dynamic environments. Ethical implications of tabular automation deserve careful consideration. Structured data may appear neutral, but as mentioned earlier, it often reflects biases in collection, measurement, or sampling. Automating analysis without addressing these biases risks reinforcing inequities. For example, a biased dataset on credit applications could lead to unfair lending recommendations if analyzed uncritically. Ethical design requires auditing data sources, disclosing limitations, and embedding fairness checks. Transparency is also key. Users must understand how results were derived and what assumptions underpin them. By embedding ethics into tabular reasoning, organizations ensure that automation serves justice as well as efficiency. The ethical dimension transforms tabular reasoning from a technical exercise into a social responsibility. The future outlook for tabular and spreadsheet reasoning points toward deeper integration of numerical and statistical skills. Current models excel at surface-level tasks but struggle with rigorous quantitative analysis. Future systems may incorporate advanced mathematical reasoning, probabilistic inference, and domain-specific models that support scientific or financial rigor. This evolution will move AI beyond formula generation toward full-fledged analysis engines, capable of supporting decision-making with statistical depth. Such systems could not only answer queries but also assess confidence, suggest alternative interpretations, and warn against misleading conclusions. By embedding numerical intelligence, tabular reasoning systems will become trusted partners in fields where precision and accountability are paramount. The trajectory suggests that the next generation of AI will blend structured logic with statistical reasoning, creating systems that are both flexible and rigorous. As structured reasoning advances, it is natural to see how it connects to mathematical and symbolic tools that extend the same principles. Just as tables demand accuracy and precision, so too do symbolic reasoning tasks in algebra, logic, and scientific modeling. By building trust in tabular reasoning, AI lays the groundwork for adopting similar systems in other structured domains. The bridge from spreadsheets to symbolic mathematics reflects a shared foundation, the translation of human questions into formal, reliable outputs. This continuity shows that structured reasoning is not a niche but a core trajectory for AI development, with applications that span enterprise, education, science, and beyond. Tabular and spreadsheet reasoning, therefore, represents a specialized but vital area of artificial intelligence. It transforms rows and columns into accessible, interpretable insights, bridging natural language with structured logic. Through formula generation, SQL query writing, data transformation, and summarization, these systems support a wide range of applications, from business intelligence to healthcare. Their efficiency makes them attractive for large-scale enterprise use, while their risks, hallucination, bias, and limitations in statistical reasoning remind us that oversight is essential. The field's direction points toward greater integration with agents, symbolic systems, and statistical models, ensuring that AI becomes not just a generator of formulas, but a reliable partner in structured analysis. By advancing this capability responsibly, we ensure that the everyday tools of finance, science, and education are enhanced with accuracy, accessibility, and fairness. Thanks for tuning in to the Bare Metal Cyber Prepcast, your trusted source for cybersecurity news and insights. Remember to subscribe at baremetalcyber.com so you never miss an update. And visit cyberauthor.me for best-selling cybersecurity books that equip you with expert knowledge. Until next time, stay secure and stay vigilant.